Hi. Since we have very little time, I'm just going to give you a very brief idea of what the double copy is and how it might help in doing better calculations, more high precision calculations for the gravitational binary problem. Let's start off with this gravitational two-body problem. You heard a little bit about the effective field theory from Ricardo, where what you do is you write down an action consistent with the symmetries of this problem. You set up a perturbative expansion with Newton's constant, and then you calculate classical equations of motion and gravitational radiation emitted. Okay, this all sounds very straightforward because and you also presumably think that the gravitational perturbative expansion will be a good expansion because we know gravitational force is weak and so on. And then you declare victory, but of course not. Otherwise, you wouldn't be having this conference, and that's because you run into this perturbative mess. Okay, so what happens is that one way of organizing this perturbative expansion is through these Feynman diagrams. And when you calculate these Feynman diagrams, you end up with a lot of vertices. So all your diagrams are made up of vertices which look like that. And I've just drawn 4 of them, but now there are infinitely many of them. And this benign looking one here has about 100 terms in it. And so you can imagine the proliferation of vertices, the proliferation of diagrams, and then you run into this big mess. So as any self-respecting physicist would do, when I run into a mess like this, there are many brave souls who have come before me who have plowed through this perturbative mess and calculated various things, but I'm just going to say this is too tough a problem, so I'm going to replace it by another problem. And that's the Yang-Mills two-body problem. So this is the same setup, except that now, instead of gravitons being exchanged, gluons are being exchanged, which are spin 1 particles. You set up a perturbative expansion in G, which is the Yang-Mills coupling constant. You calculate the classical equations of motion, and you calculate the gluon radiation that's emitted. And then you see that the kind of diagrams that you get will have only 2 kinds of vertices. Okay, so it has a 3-point vertex and it has a 4-point vertex. And this 3-point vertex, however you count, has just 6 terms. And in fact, you can go to another gauge and get 3 terms instead of 6 terms. And so this looks like an enormous simplification over the gravitational problem. But you might say that, okay, you are trying to solve some problem, you're trying to search for something somewhere, and it's dark there, so you go just search where the light is, and that's not fair. Well, the point is that there are these amazing relations that were discovered by Byrne, Carrasco, and Johansson, and what they said is that if you're computing a quantum scattering amplitude, let's say you're doing a n-point tree-level amplitude, it's a complicated object, but I'm just going to spell out the structure of it for you. And this has, in the numerator, you see n alpha times c alpha n alpha times c alpha, where n alpha is where all the velocities go, where all the kinematics of this problem goes, and c alpha is where all the color factors go. So there's an underlying gauge group here, and all the color factors which belong to that gauge group go into the c alpha. And what happens is you can arrange the n-point tree-level amplitude into a sum such that every 3 terms satisfy this identity, okay? And this identity comes from the Jacobi identity of the underlying gauge group. The remarkable fact that these guys discovered is that this thing can be arranged such that these n alphas also satisfy the same identities. And what you merely need to do is replace the c alphas by the n alphas, which is replacing the color by kinematics, and you go from an n-point tree-level Yang-Mills amplitude to an n-point graviton amplitude. These relations have been proved for all tree-level amplitudes, and they've been used for many loop-level amplitudes in various contexts. So the main point here is that it seems like all that was relevant was the cubic structure of these Feynman diagrams. So why not go all the way? Why not have something which just has just a cubic structure? And that's a theory of a scalar. And this scalar has just a 3-point vertex that comes from this term here, which looks like an FABC times an F tilde ABC. Now these Fs are structure constants which belong to the underlying gauge group. This scalar takes values in the adjoint representation of a G cross a G tilde, two independent gauge groups, and it has only this one 3-point vertex. Okay, so how does this help us? Firstly, let me just quickly summarize what has happened. So you started off with the theory of gravity, which has gravitons which are spin 2 objects. And if you're looking at the degrees of freedom, in this case, you have sources which are traveling on some world lines. They are emitting radiation, so you have the degrees of freedom of the trajectory. You go down to your Yang-Mills theory, which is a theory of spin 1 particles. The degrees of freedom there are trajectory and color charge. Okay, the color charge is a generalization of charge that you might know and love from electrodynamics. You go down further, you get a theory of a scalar, and this degree of freedom has, the degrees of freedom here are trajectory and two kinds of color charge. Now, what we get inspired by the BCJ construction that I just showed you, and what you do is in this theory, you look at all the color that comes from one gauge group, and you replace it by the kinematic factors, and you go up to Yang-Mills. In this theory, you have color times kinematics, and you replace all the color guys by the kinematic guys, and you go up to gravity. So that's the sort of prescription we're going to follow. And I'm not going to show you too many results because we don't have time, but I'm just going to state what the answer is. What happens is when you do this, and we do this to find leading order radiation when two sources are being scattered. We are not restricted to two sources. We can go do n sources, or we can do d dimensions. But the result is that you can compute the biot joint scalar radiation and do the color kinematics replacement, get Yang-Mills radiation, do another color kinematics replacement, and get graviton radiation. So this was done by Goldberger and Ridgway in 2016, and then I had some work with Goldberger and Thompson in 2017, which completed this picture. I'm going to quickly tell you a little bit more about the extensions to this work. Bound sources, radiation from bound sources was done in this paper. We extended this to spinning sources, where we computed the radiation, the leading order radiation from spinning sources in this set of papers. And this whole setup has been taken to the next two leading order in radiation in this nice paper by Shen, where also the Jacobi identities that I was talking about show up. There are other approaches to this problem, which also are called the double copy. And that's the Kershail double copy. You heard a little bit about Kershail coordinates in Shiraz's talk. And this was actually the first context in which the double copy appeared in classical calculations, where they showed that you can sort of understand the Schwarzschild solution is coming from a Coulomb solution. And there are various extensions of this idea to various things, which I won't have the time to talk about. And also you can then ask what is the relation of this classical double copy to the scattering amplitudes picture that I talked about. And that's currently being investigated by a bunch of people. This paper here, which was recently published, recently put out on arXiv, has some ideas about how to prove the classical double copy starting from the BCJ double copy. And there's also in the soft limit, there's some ideas of how to prove it from this color kinematics duality, which is also a recent paper. And I'm just going to end with a couple of comments about how this might possibly be useful for LIGO. It would be, so one caveat that I didn't mention is that in the gravitational theory you end up with, you don't just get the graviton, you also get a dilaton. And you have to come up with a way to remove the dilaton, and there are some ideas for doing that. You have to go to higher orders, of course, to get to the kind of calculations that might be useful for LIGO. And here it might be useful to combine various new approaches that are being used to solve this kind of problem. Some steps have been taken in these works here. And then you can also ask the question for, sorry? It's 2 p.m. Okay, I'm sorry, there's this typo. There's a 2 p.m. and the 3 p.m. potential that Ricardo talked about. And then you can ask if this also works for curved spacetimes, and you might say that this is actually maybe also a little bit relevant to the LIGO problem, because you heard about the case of extreme mass ratio in spirals, where you would want to do a perturbation about some general background spacetime. Thank you.
I mean, in all this sequence, you have to choose this double copy of two gauge groups in the scalar field. General relativity has not heard of this gauge group. So what gauge groups do you have to choose in order to get anything which has to do with general relativity?
Yeah, surprisingly enough, it looks like we are agnostic to the choice of the gauge group, because it's a formal replacement of the color to kinematics, which actually is agnostic to what gauge group you're using, at least at the orders that we've computed. It just matters that there is a gauge group and there's an underlying Jacobi identity.